Hello everyone. So in today's video, what I want to take a look at is how we can start to perform some operations with algebraic vectors. The examples I'm going to use are in 2 dimensions only because it's easier to visualize, but these rules that you will develop will easily extend then to 3-dimensional vectors as well. So in the first example, what I want to look at is how we would add these 2 vectors together. So if I have vector u, here it is, components 2, 5, vector v, components 3, 1. What I want to look at then is what happens if we add these 2 vectors together. In other words, what happens if I try to do vector with components 2, 5 and add that to vector v with components 3, 1. What's the result? So what I'm going to do is just go back a few lessons and say, well, if I want to add vectors, really what I want to do is create that path. We talked about that parallelogram rule, the idea that I could take this vector u and slide this over here. So that's what I'm going to do and say, well, there is also vector u. And then what I'm going to do is follow that path. So from O, follow the arrows, okay, from the tail to the head of the path, and we end up with this resulting vector here. So if I add u and v together, here is our resulting vector, u plus v. So if we look at that resulting vector, what we see then is that its components now will be 5 and 6. So the answer here is 5, 6 for its components. But if we look closely, we can see hopefully quickly where that is coming from. All we're doing is taking the x component from v, which is 3, and we're adding on the x component from u, which is 2. If I add those two together, there it is, we get 5. Likewise here, if I take the y component for v, which is 1, and then I take the y component from u, which is 5, and I add them together, I get this value 6. So all we have to do is just add these components together, and we can see graphically why that would make sense. We can also take an algebraic approach here. So to do that, what I'm going to do is write these 2 vectors out using the basis vectors. So 2i plus 5j. And if I add 3i plus 1j, okay, and now we just use our rules that we would use for algebra, which we said vectors often just use the same set of rules. I can just collect my like terms, and we end up here with the exact same answer, 5i plus 6j. So we can see how algebraically, using the basis vectors, this makes sense, and using our components here, we can see why this on our graph would then also make sense. In general then, we could extend this to vectors in 3 dimensions. So if I define vector u as a1, b1, c1, and vector v as a2, b2, c2, then if I add these together, we would end up with components a1 plus a2. I just add the components together, and likewise for the b's and the c's here as well. And there's our resulting vector. We can also take a look at what happens if we do scalar multiplication. Scalar multiplication is when I take a vector and I multiply it by some scalar number. So if I do that, if I have 2v, we can take a very similar approach and say, well, if I have 2 of these, then I need to draw a second v and say, well, there is then 2v, v plus v, or 2v. So again, our graphical representation would give us then 2v is the same as 2 times this vector with its components, 3, 2. And we see that the answer here is just that we're going to now get 6, 4. In other words, all we've done is distributed that 2 to both of the components. So up here we have added the components. And here we'll say multiply components by the scalar, or by that number out front. Again, we can also confirm this then algebraically We can say 2v, if I write this using our basis vectors, this would be 3i plus 2j. And if we distribute the 2, we end up here with 6i and 4j using our algebraic skills, and we end up with the exact same vector. So if I take any vector, 2 dimensions are now 3 dimensions, and I multiply by some scalar, scalar is just some real number, then our result here would be MA, MB, MC. We just multiply each component by that scalar. So in our example here then, I have vector u and v. I've given it to you using the standard basis vectors. What we're going to do here is figure out, well, what is 4u minus 2v? So we're going to start to apply some operations to these algebraic vectors. If we do that, I'm actually going to write this out because it's a little bit less writing to use its component form. Okay, so I'm going to rewrite this as 3, 2, negative 4. I'm going to rewrite this as 5, negative 2, negative 6. So if I want now 4u minus 2v, this would be equivalent to 4 times vector u and minus 2 times vector v. We can now combine these rules together. We have a scalar here, so I can distribute the scalar. This will give me 12, 8, negative 16. I'm going to say plus because I'm going to distribute the negative 2 here, so that would give us negative 10, 4, and 12. And then we can add components together. So if we do that, we end up with 2, 12, and negative 4. Once I create that, we could now apply some of the things that we've done in the past. How do I get the magnitude of that vector? So from previous lessons, remember magnitude here is really just coming from Pythagorean theorem. So the magnitude of the vector is equal to the square root of 2 squared plus 12 squared plus negative 4 squared. And if you work that out and reduce that on your calculator, you will end up with 2 times the square root of 41. So there is how we can then add vectors or multiply them by a scalar. Last scale that I want to take a look at is what we call point-to-point vectors. So a point-to-point vector is if I give you 2 points on a graph. In this case, I've given you points A and B. The question is, how do I create this vector then AB from those 2 points? So first, our visual. If I want to create vector AB, keep in mind that the order is important. This is saying we're going from A to B. So in other words, A is the tail, B is the head of the vector. We're going in this direction here. Remember, to create this vector AB, what I really need then is what is the X and the Y component. Okay, we like to often draw vectors starting from the origin. Remember, we call those our position vectors. But I can really draw a vector wherever I want on the Cartesian plane, and the components of that vector are really just describing how you are moving horizontally and then how you're moving vertically. So in this case, to get from A to B, I would have to move horizontally to the right. We can see that as 4 spaces. And vertically, I would have to move down 2 spaces. In other words, that is negative 2. This should look familiar, at least in 2 dimensions, because really what we're doing here is the same thing we did back in grade 9 when we were calculating slope. We're getting rise and run. The only difference here is I don't call them rise and run. Now I'm going to call this the X component for this vector. I'm going to call this the Y component for this vector. So visually, we can see this on the graph, but I don't always want to have to draw this. So I'm going to come back here like we would do with slope and say, well, how could I get those values? Well, if I want to get this horizontal component, remember if I was doing slope, what I would do is take x2 minus x1. So really it's just the difference between these x coordinates. Take the 5, subtract off the 1 tells you that that would be 4. So I'm going to say 5 minus 1. Just like our slope, it's the second point minus the first point. So 5 minus 1 gives me my x component. Likewise, for my y component, again, I want to go from A to B. So I start with my b component, and I'm going to say 2 minus 4. And we'll see that we end up with the exact same answer that we could visualize on the graph. There is our vector with components 4 and -2, 4 to the right and down 2. If I was to extend that in 3 dimensions, much more difficult to visualize as you try to draw in 3D, but we can very easily extend that idea. If I want vector AB, I take second component minus first component, sorry, not component, these are points, second coordinate minus first coordinate, that'll give me the x component for the vector. I can do coordinate here, so y2 minus y1, that'll give us our y component here. And then lastly, I can do z2 minus z1, these are the coordinates for the point, and when I subtract them, that would give me my component for the vector. So there is our new vector AB. If I flipped it around, if I wanted vector BA, then we would have to flip the order here. So order is important, be careful as you're doing that. So last example then, I want to show that I have 3 points here in 2 dimensions, P, Q, and R. I want to show that they are collinear. Collinear reminder just means that these 3 points, if I was to graph them, would fall in a straight line. And one way to do that is to use vectors. So I've made a note here and said, well, 3 points are collinear if the vector from P to Q and the vector from Q to R have the same or opposite direction. Again, trying to visualize why would that work, okay? If I draw a line with 3 points here, if I put P, Q, and R, if they are collinear, then that means this vector from P to Q must be in the same direction as Q to R. They might be in opposite direction if I was to say draw it this way instead. If I put, say, Q down here, put P here, and put R here, and then I would have vector PQ pointing this way, vector QR pointing this way. So we don't know what order the points go in. So as long as they're either pointing in the same or opposite direction, I know that they would be collinear with each other. One way to show that they are collinear then, we did this several lessons back, is this idea here, that the one vector must be a scalar multiple of the other. Okay? And we can show that something has the same or opposite direction by doing that. So what I'm going to do here is create that vector PQ. So again, a point-to-point vector is what we call it. I want the vector that goes from P to Q. So to do that, we subtract coordinates. Okay, -1 minus 5. And 5 minus 1. Creates this vector PQ, -6, 4. I'm also then going to create the vector then that goes from Q to R. So if I do that, Q to R would be 11 minus -1. So I'm going to write that as 11 plus 1. And I would have -3 minus 5. So if I do that, I end up with this vector 12 and -8. Now, what I'm trying to show then is, do these have the same or opposite direction? In other words, can I write one as a scalar multiple of the other? And this comes partly from observation. Can we see what would you multiply by? You could pull out a calculator if you really need to, but I think here we can see that if I multiplied this by -2, okay, we would end up with this new vector QR. So for my conclusion, I'm going to say here then, since QR is equivalent to -2 times PQ, therefore these 3 points, so P, Q, and R, are collinear. There we go, collinear. Okay. Try some of the homework. Let me know if you're having any difficulties. Send me an email, or if you want, we can set up a phone or video conference, and I can work through some of this with you. Have a good day, guys.